Hi everyone. In this video we're going to cover section 2.3, characterization of invertible matrices. So in the previous section we introduced what it means for a matrix to be invertible, and in 2.3 we're not going to do too much computation really, but really introduce an underlying theorem that is hugely consequential to this course. And it's theorem 8 called the invertible matrix theorem. And what it does is this theorem ties together everything that has been introduced thus far in chapters 1 and 2, and in other texts it's called like the unifying matrix theorem or something like that, because it is a unifying concept in linear algebra. Okay, and so what it says is that all of these statements A through L are equivalent to each other, logically equivalent. That is, for any of the statements given a matrix A, these statements are either all true or all false about that matrix. And pause the video, and you can read through each A through L statements just to kind of familiarize yourself with some of the things that we saw earlier in chapter 1, or re-familiarize yourself. And then I'm going to explain how we go about locking or tying all of these statements together in saying that they're either all true or all false. And the first thing that I want to mention is the word implies. So I'll put it in quotes, implies. Okay, and when we do proofs in math, right, we say, well, if this thing is true about my matrix A, then that thing is true about my matrix A. If, for example, if A is true, then B is true. Like, so we assume A is true and have to show why that means that B is also true. And so the way that we can kind of simplify that sentence in like English language sentence is using the word implies. A implies B. The truth of A means that B is also true. B implies C. The truth of B means that C is also true. All right, so the way that we tie these, I believe there's 12 of them, there's 12 statements together, is like this. All right, and it's kind of a little funky picture here, but we say, all right, this is the way that the text does it, and it's kind of the most efficient process to lock all of these statements together. And I'll go through part of the proof, not all of it, but I encourage you to read through it in your text also. And what we'll do with the proof is start out with A, the statement A, and we'll say if A is true, then I can say that A implies J. If J is true, then I can show why J implies D, which implies C, which implies B, which implies A. And that's a pretty efficient loop to go through, and we have to close that loop because B needs to show that A is true, D needs to show that C is true, etc., etc. So that has to be a closed loop. And then we tie in, statements K and G in this little triangle here. The truth of A implies K, which implies G, which implies A. And then these last three over on the right, these are all if and only if statements. Okay, so I don't need to connect these in a loop in a triangle because the if and only statements have arrows on both sides. They imply each other in both directions. Okay, so let's now take a look at a little bit of a look at how the proof works. And some of them are a little bit easier to understand, the logic. Others are a little bit more involved. And we start out with one that hopefully is pretty easy. And we're going to say if A is true, then J is true. So why is this, right? A says that my matrix is invertible. How do I know that if my matrix is invertible? Now I'm looking at J. There is a matrix C such that C times A equals the identity. So this part of the proof is one step. We're going to say, so I'll put a little colon there, if A is true, if my matrix is invertible, if A is true, then the A inverse that exists, A is invertible, is equal to the matrix C. Boom, done. That gives me J. C times A equals the identity. A inverse times A equals the identity. That's all we need to say for that step. Next, we get one that is a little bit more involved. All right, J implies D. If C times A equals the identity, what we're going to do is we're going to say suppose that J is true, or suppose that CA is equal to the identity matrix. And then we'll say if some vector x satisfies ax equals 0. Because, by the way, remember, we're trying to show that the equation ax equals 0 has only the trivial solution. That's what D says. Okay, so if x satisfies ax equals 0, then c times a times x on the left-hand side equals c times 0 on the right-hand side, which is 0, and x is equal to 0. So that means that ax equals 0 has only the trivial solution. X has to be the 0 vector. That's the only possible solution to that matrix equation. And that gives us D. Like, that's the end of that step of the proof. Okay, let's keep going here. Let's go to D implies C. All right, so now for this step, we're going to say, suppose ax equals 0 has only the trivial solution. Only the trivial solution. That's what letter D says, and we need to show why A has n pivot solutions, or n pivot positions. So if this has only the trivial solutions, this means A has no free variables when it's reduced to or when it's in reduced echelon form, and A has n pivot positions, n pivot columns, I'll say, since it is n by n, right? That's what we're told right from the beginning, that it is an n by n square matrix. And that is the goal of that step of the proof. We have shown what we need to show, that A has n pivot positions. Now let's do the next one. We're going to go to C. Oops, C, there we go, implies B. If C is true, so we're going to say if A is square, oops, capital A because I'm talking about the matrix, if A is square and has n pivot positions, because that's what C says, they must lie on the main diagonal. They must lie on the main diagonal, and the reduced echelon form and the reduced row echelon form of A is the identity matrix, right? It has n pivots. They have to be on the main diagonal. Boom. That gives us what we need to show in that step of the proof. All right. And the last one to close this loop is already something that's been shown earlier in the text. So this is a fairly anticlimactic ending to this part. But to show that B implies A, this is already stated in Theorem 7 in section 2.2. So we don't need to say it again if we've already shown it. Okay, so that is just the first loop of the invertible matrix theorem. Pretty cool stuff that we can tie all of these statements together with fairly short, brief little logical arguments, and then all 12 statements. You show me any square matrix, all 12 of them are either true for that matrix or false for that matrix. Okay, I encourage you to read through the rest of the proof in the book, but that's all that I want to include in the video today. So then the question is, how do we use the invertible matrix theorem? Like, what do I do with it now that I know that this thing exists? So I have a matrix A here, and we need to use the invertible matrix theorem to decide whether or not A is invertible. And one option that I have is to use the tools that we've already gained in this course and say, all right, let's do some row operations. Let's say I use my leading one to eliminate the zeros below it, and we would end up with a matrix that looks like this: 0, -1, -1. right? Do I know anything now that in the invertible matrix theorem that says whether or not this matrix is invertible? Not yet, but if I do one more step and add rows 2 and 3, then I think we'll know our answer. 0, 1, 4, 0, 0, 3. Okay, so now I'm in echelon form, not reduced echelon form, but I can say A has 3 pivot positions and is therefore invertible by the invertible matrix theorem. Invertible matrix, that's a terrible M, matrix theorem. So I'm just abbreviating that there. And that is actually, let me put it in parentheses there, part C of the invertible matrix theorem. Okay, so I could have done something different, right? I could have augmented with a column of zeros and shown that only the trivial solution exists. I could have put it in reduced echelon form and said, hey, it looks like the identity. It's row equivalent to the identity. That's in the invertible matrix theorem. We can use any of those statements from that theorem to draw our conclusion about whether or not A is invertible. In the next part of the section, we go back and talk about our language involving linear transformations, right? So if I have my vector x and I multiply it by a, that maps it onto a times x, right? If I multiplication by a is that linear transformation that we talked about previously. Well, if A inverse exists, A inverse is the linear transformation that maps me back onto my vector x. So if my matrix is invertible, right, then we can undo that linear transformation. And then this is how we kind of show that formally. Notice here our transformation has to take us from Rn to Rn, because it's an n by n matrix, right? S of t of x, S is my inverse transformation, t of x is just the transformation, maps back to x for all x in Rn, and the opposite order maps me back onto x for all x in Rn, right? That is just how we use the language of linear transformations when talking about inverse matrices. And you can read through Theorem 9. I'll let you do that on your own. And now our last example for the section says, what can you say about a one-to-one linear transformation, T, from Rn into Rn? All right, so we go back and think, what does it mean for, how do we connect one-to-one transformations to the terms and the topics within the invertible matrix theorem, right? So if you go back to Theorem 12 in section 1.9, go back and look it up. So we'll say that one-to-one implies that the columns, switch those two letters, the columns of the standard matrix, A of the transformation T are linearly independent. They are linearly independent. And again, that is Theorem 12 from section 1.9. Section 1.9. Okay, so what that means, because I have connected the term one-to-one back to the concept of linearly independent, which we already established that back in section 1.9, and linearly independent, hey, that's on the invertible matrix theorem. This means that A is invertible. A is invertible by the invertible matrix theorem. By the invertible matrix theorem. And it tells us even more about that transformation. And T, the transformation, maps Rn onto, right? That's also in the invertible matrix theorem, that my transformation is onto. And, so another and, T, the transformation, is itself invertible. Okay, so it gives me every piece of the invertible matrix theorem being true about the matrix A for the transformation, as well as the transformation T itself. All right, so a little bit more theory, conceptual stuff in this section. Take the time to digest it, read through the text, let me know if you have questions, and get started on the homework. Thank you for listening and have a wonderful day.